Welcome to lecture 8 of the course. In this lecture, we will continue our discussion on the density operator formalism or the density matrix formalism to represent the quantum state of a system. In this lecture, we will also discuss about the so-called optical block equation. So let's begin. In the last class, we discussed how to represent the quantum state of a system by using the so-called density operator, and we have defined density operator by this relation where P alpha is the classical probability here, and this density operator can be represented in the form of a matrix as well. For example, for the case of a two-level system, it is going to be represented by a 2 by 2 matrix, and this definition can be extended to a n-level system as well, where this density operator can be represented in the matrix form by n matrix. And this is how we can represent the matrix element of a density operator or a density matrix. Also, we learned that trace of rho is equal to 1 because the diagonal element in the density matrix basically represents the population, and on the other hand the off diagonal element represent coherences or the relative phase between two states. And also we learned that rho is equal to rho Dagger. That means the density operator is a Hermitian matrix, or density matrix is a Hermitian matrix. We also learn how to quantify a quantum state, whether it is a pure or mixed, using density operator. If we find that rho square is equal to rho or trace rho square is equal to 1, then that is a pure state. On the other hand, if we take trace of rho square and we find that it is less than 1, then this is a mixed state. Now let me discuss about one very important usefulness of density operator. One can use density operator to find expectation value of an operator. Let's say operator A, its expectation value is going to be given by trace of rho into A. Okay, density matrix, if you multiply with the operator, because you know the operator can also be represented by matrix, and if you take the trace of the product of the matrix, that is going to give you the expectation value of an operator. And this is very useful in many calculations, as we will see in our problem solving session as well by doing some examples there. First, let me actually prove this relation very quickly. We are considering a system or a quantum state which is a pure quantum state. In that case, say I have this expectation value of operator A is basically psi A psi, right? That's in the state vector representation. If I want to find out the expectation value, then this is what I write, where get psi is the normalized state vector. And if I now use the orthonormality condition, I can always use this orthonormality condition which we have discussed. Say ket k bra k sum over k is equal to identity. This I can put anywhere because it is identity. So let me put it inside here. Let me put it here. So this is going to be ket k bra k, then a is there, okay, and then psi is there, and then summation sum over k. So this is what I am going to have here. Let me tell you that I have used the so-called completeness condition, and this now I can do because of the fact that this is just a number. Okay, I can take it this side and then I can write it in this form. So let me write here this, let me take this side. So I have k a psi, k psi, and then this number I am putting this side. Now you can recognize that this quantity is nothing but rho, density matrix or the density operator. So therefore I have k sum over k, k a rho, and I have k. So as you can see, this is nothing but this is the matrix multiplication of the density operator and the operator,
and then I'm taking the sum over k. That means I'm just summing up over the diagonal elements. So therefore this means that I have this expectation value of a is equal to trace of, I can write it in this way also, row A or A row, doesn't matter. So expectation value of operator A is simply given by taking the trace of the product of the density matrix and the matrix form of the operator. Okay, now let me make some comments about the time evolution of the quantum state. We note that the state vector k psi evolves according to the time evolution is given by the Schrodinger equations. Now, what about the time evolution of the density operator rho? Because density operator also represents a quantum state, we can quickly find out. To do that, let me consider again a pure state. Rho is equal to k psi bra psi. And if I take a time derivative on both sides, then I am going to have del rho del t is equal to del k psi del t bra psi plus k psi del t of this bra psi, right? And because of the fact that this Schrodinger equation I have, if I take the complex conjugate of this, then this is actually going to give me minus I s cross delta bra psi delta t is equal to bra psi and the Hermitian conjugate of this Hamiltonian, but because the Hamiltonian, it's a Hermitian matrix, so S dagger is equal to H, so I can simply write it in this form. And now I can utilize this expression as well as this one here, and then what I will do, you can easily make it out. I will have del rho del t is equal to, I will have 1 by I h cross. H cross is the reduced Planck's constant, I am sure you know, and this is H, this part I am writing, and you have H psi here. Okay, this is what I have, I am taking it this side, and then this is what you have, 1 by I s cross H k psi, then you have bra psi. Then if I go to the second part, then you have here k psi is there, and here I am going to have 1 divided by minus I h cross bra psi h, right? So this is what I am going to have, and this I can write as, if I take 1 by I s cross common, and this is going to give me, this guy is nothing but your rho, right? So this is rho, so I have here h rho, then I have minus, because of this minus sign, then again I have rho h. So this is what I have, and this whole thing, as you can see, I can write it as del rho. Actually this is operator, so let me put the operator sign. Del rho del t is equal to minus I by h cross, and this is the commutation relation between h and rho. Okay, so this is how for an isolated system the density operator evolves with time, and this equation is referred to as Schrodinger, not Schrodinger equation, rather it is called Schrodinger von Neumann equation. Schrodinger von Neumann equation. By the way, note that an operator A representing a physically observable quantity obey the so-called Heisenberg equation of motion. Now, if you look at the evolution equation for the density operator, we have I h bar del rho del t is equal to h rho. Okay, now if you look at both this equation, Heisenberg equation and the Schrodinger von Neumann equation, you will immediately see that the density operator is not obeying the Heisenberg equation, and that is because rho, or the density operator, does not represent physically observable quantity, rather it represents a quantum state. Okay. Now, let me discuss two-level atom once again using the so-called density matrix formalism. In lecture 4, we wrote the Schrodinger equation describing a two-level atom where we had this two-level atom was represented by a ground state it has and an excited state, and the resonance frequency is omega 0, that is the difference of the energy levels. And we discussed there that a classical electromagnetic field, a light field, is getting incident on the atom, and it is incident at the location of the atom is at z is equal to 0, and the electric field of the light field has a frequency omega, which is detuned from the resonance frequency of the atom by an amount delta, where delta is the detuning parameter. We wrote it as delta is equal to omega minus omega 0. And this electric field is the classical electric field. And again, let me remind you that here we are treating the electric field or light field as a classical object, where the atom is a quantum object, and that's why this domain of quantum optics is known as the semi-classical quantum optics. So this is the electric field for the light field. And in the state vector representation, the Schrodinger equation is is cross delta psi delta t is equal to h psi, and this k psi, arbitrary state of the atom, is in a superposition of the ground state and the excited state. So kg and kt are the basis states. And also you recall that the total Hamiltonian was given as h0, that is the component for the isolated atom, and then there is a interaction term between the atom and the field, and isolated part when the atom is not interacting with the field, that was given as s cross omega 0 kt bra e. And here we have taken the ground state energy to be 0, you can recall, and under the rotating wave approximation we have written the atom field interaction part as s cross omega by 2 sigma e to the power I omega t plus sigma dagger e to the power minus I omega t, where sigma is the atomic lowering operator given as kg bra e. Okay, and omega is the so-called Rabi frequency. So if you have forgotten, please refer to lecture number 4 once again. Now we can write this Schrodinger equation in the density operator formalism as well, by using the so-called Schrodinger von Neumann equation. Just a while ago I mentioned it, so let me write it once again. The Schrodinger von Neumann equation is delta rho delta t is equal to minus I by s cross, commutation between the Hamiltonian and the density matrix or the density operator, where this h is equal to h0 plus haf, atom field interaction part, and rho is the density operator, is now it is k psi bra psi, and because it is a two level atom I can write it in the form of a matrix, a 2 by 2 matrix, where let me write it as rho zz, rho ze, rho ez, and rho ee. Okay, now you just see here that here I am writing the ground state in the upper row here. Okay, so just we have to keep this thing in mind, because in some representation we may write here the first row first column element by this term also, but I am taking now writing the ground state part only. So I am going to stick to this convention here. Once I choose this one, then accordingly I will also represent the Hamiltonian later on, as you will see when I'm writing. Basically why I'm saying this, because when I'm going to write the Hamiltonian I have to be careful how I am writing my density operator. Okay, because I'm now writing the ground state in the upper row and in the first column for the ground state part. Okay, let me now once again discuss about the fact how to describe the dynamics. And already we have discussed that the dynamics become easily tractable if we go over to a rotating frame of the laser field. And from previous lecture we saw, actually lecture 4 I think, or lecture 5, that if we go over to a rotating frame of reference, the state vector becomes psi tilde is equal to cg kg plus ce tilde kte, where you recall that ce tilde is equal to ce e to the power I omega t, and this Hamiltonian now take the form h tilde, and it would become minus h cross delta kate e bra e, plus, because we have gone to the rotating frame, by doing that now we are able to get rid of the time dependent part, explicit time dependence part. So sigma plus sigma dagger, that's what we are going to have. And delta, once again let me write it, it is omega minus omega 0. And the corresponding Schrodinger von Neumann equation is delta rho tilde delta t is equal to minus I by h cross h tilde rho tilde. Okay, so this is the equation now we are going to deal with. Here rho tilde is equal to kth psi tilde bra psi tilde. Let us work out the equation of motion for each of the density matrix element. Let me write the explicit form of the density matrix for rho tilde, that is rho tilde zz, rho tilde ze, rho tilde ez, and rho tilde ee. And this operator h tilde, which is the Hamiltonian, in the matrix form it is going to be h cross. Now here you see I am going to write 0 because that refers to the ground state, and I am doing that once again, let me remind you, because I have written the density matrix in this way. Okay, first the ground state thing, that's why I am going to write it like this, and the off diagonal elements are capital omega by 2 minus delta here. Okay, so this is my h tilde. So what I'm going to do now, I'm going to find the commutation between h tilde rho tilde. I have to open the whole term, so it's just mathematical algebra. I will just show you few steps, then you can make it out yourself. So you'll have h tilde rho tilde minus rho tilde h tilde, and h tilde is h cross 0 omega by 2 minus delta. Rho tilde is rho tilde zz, rho tilde ze, rho tilde ez, rho tilde ee. Then minus, we are going to have minus h cross. H cross is coming from h tilde, by the way. And then here rho tilde, this term I am having rho tilde zz, rho tilde ze, rho tilde ez, rho tilde ee, and h tilde part will give me 0 omega by 2 minus delta. Now if you do the algebra carefully, just matrix multiplication only, it is going to give you h cross omega by 2 rho tilde ez minus rho tilde ze, and in the second column you are going to have omega by 2 rho tilde ee minus rho tilde zz plus delta rho tilde ze. Please verify yourself. And then in the second row, first column, you are going to have omega by 2 rho tilde zz minus rho tilde ee minus delta rho tilde ez, and second row, second column, you will have omega by 2 rho tilde ze minus rho tilde ez. So this is what you will have, but this is actually equal to I h cross delta rho delta t, right? Because this is what the equation you have. Okay, so this guy is equal to I h cross, you have delta rho zz delta t, delta rho ze delta t, delta rho tilde EZ delta T, delta rho tilde EE delta T. Now, please compare the right hand side with this equation, okay, this part, and this is going to give you four equations, and let me write that. Please try to do that. This is an important equation. You will have delta rho tilde delta T minus I omega by 2 rho tilde EZ minus rho tilde ZE delta rho tilde EE delta T is equal to minus I omega by 2 rho tilde ZE minus rho tilde EZ and this is equal to minus delta rho ZZ rho tilde ZZ delta T, right, as you can see. And then you are going to have, for the off diagonal elements, you will have delta rho tilde ZE delta T is equal to minus I omega by 2 rho tilde EE minus rho tilde ZZ minus I delta rho tilde ZE delta rho tilde EZ delta T is equal to I omega by 2 rho tilde EE minus rho tilde ZZ plus I delta rho tilde EZ. Alright, so these are the four equations that we are having for the evolution of the density matrix element, and this is very important exercise, and I have done it in somewhat details. There is a reason, because this calculation, the way I have done it, can be extended to for any higher level system as well, for example 3-level system or even 4-level system and so on. And you will see later on that when I'm going to discuss about, say, electromagnetically induced transparency phenomena, which is a 3-level phenomena, the way I have done the calculation is going to be useful there, and we'll see the same procedure I am going to apply it there as well. Now these equations that describe the dynamics of the populations and coherences of the two-level atom interacting with the classical light field does not take into account the so-called spontaneous emission processes. Spontaneous emission processes. And I'm sure all of you know what I mean by spontaneous emission process, because you know that in practical or in realistic situation, even in the absence of interaction, if the atom is in an excited state, after some time it fall down to the ground state by emitting a photon. This process can be incorporated into the density matrix equation as follows. What we can do is that we can write these equations for the density matrix element describing the population of the excited state. Its time evolution would be, we can write it in the absence of interaction by this equation. As you can see, this is a rate equation and is a decay equation. A term minus gamma is there, capital gamma, and gamma is the decay rate of the excited population, and this population is going over to the ground state. So the ground state is now basically populated, so we can write it in this form, because this population is going to the ground state, so it would be plus capital gamma, and here it would be rho tilde EE, because the excited state population is going over to the ground state. And this gamma, as I said, is called the decay rate of, it is called decay rate of excited population. Excited population. And sometimes this gamma, it's also known as longitudinal decay rate. I will not go into the details of why it is called longitudinal decay rate. Maybe sometime in later class, maybe I will discuss about it. Also note that the coherence terms rho ZE and rho EZ, they also decay, and their decay can be incorporated by writing this equation. These are basically called phenomenological treatment. Rho tilde ZE decay via this equation, and this decay rate is known as it's called the decay rate of coherences, and it is also sometimes known as gamma. Small gamma perpendicular sign is just referred to as transverse decay rate. That's why this transverse or perpendicular sign is there. It's called transverse decay rate, or you can also say it as decay rate of coherences. And similar equation I can write it for the other coherence term. It is also exactly the same way, it also decay, and that is minus gamma perpendicular, small gamma perpendicular here, rho tilde EZ. All right, now this longitudinal decay rate capital gamma and transverse decay rate small gamma perpendicular are many times written in terms of, these are related to the longitudinal, this is longitudinal, let me write it once again, it is longitudinal decay rate, and this is transverse decay rate. As you can see, actually by decaying it's going into a relaxation state, so there is a relaxation time. So gamma, capital gamma, which is the longitudinal decay rate, it is related to a longitudinal relaxation time denoted by capital T1, and it is related to the decay rate capital gamma by this equation. And the transverse decay rate, it's called transverse relaxation time, and it is denoted by the letter capital T2, and T2 is equal to 1 divided by gamma perpendicular, small gamma in perpendicular. T1, capital T1 is called longitudinal. These are mostly used terminology. This is called longitudinal relaxation time, and T2 is called transverse relaxation time. Okay, now we can actually combine these damping terms for populations as well as coherences and write the full evolution equation for the density matrix equations. And then if we write it just by incorporating these decays, these are the equations that we can write. By the way, let me just tell you once again that these equations that I have written here, for example, these decay rate equations, these I am writing when there is no coupling with the classical light field. That means capital gamma is equal to 0, and also I am considering that in the resonance condition, that is delta is equal to 0. Similar is the case here. Here I am writing this equation when there is no interaction with the light field, that means Rabi frequency is 0 and the resonance frequency delta is equal to 0, obviously because there is no classical field, omega, small omega is not present. Now incorporating all these factors into account, that means relaxation time or the decay rates, transverse decay rate as well as the longitudinal decay rate, I can add these terms and then I can write the density matrix equation in this form, and this form of the equation are known as optical block equation. These are popularly known as optical blots or block equations. Okay, and these are very important set of equations, and we will come back to these equations again in a later lecture.
Let me stop here for today. In the next lecture, we are going to do some problems based on lecture 7 and lecture 8. See you then. Thank you so much.